Hello, everyone, and welcome to today's free public webinar with TPC Training entitled Learning Electrical Troubleshooting in a Virtual Environment. My name is Ryan Smith. I am a product manager of our instructor-led training here with TPC, and I'm joined by Greg Sutton today, one of our TPC training instructors. He has lots of experience training technicians and people around the industry in learning about electricity, both in the classroom and also in the virtual environment. So we're going to really focus on that second one, the virtual environment, in today's free session today. So the goal for today's session is really just to be a snippet, a small chunk of our electrical troubleshooting course that we give, and to run through a couple of the exercises that we go through in that course to give you an idea of what this is like in the virtual environment. So before we get started, I'd like to let everyone know that today's session is being recorded, and it will be available on the TPC Training website within about 2 business days of this event here on September 10th, 2020. Also, I wanted to let everyone know that this is a live event right now, and that is to say that we can actually ask questions on the Q&A line, and I really highly recommend that you all do. So if you look at your toolbar, you should see a couple options there, including Q&A. So you'll see a chat. I try to avoid using the chat because we won't be able to see those questions and tailor them and prioritize them for you. So click on the Q&A session there, and when you click Q&A, you can ask any questions you like, and we'll be able to answer them at the tail end of the session. We'll spend as much time as we can to fill the hour in answering your questions. So we're really looking forward to that. And I guess the first thing we're going to do as a group before we get started is to learn a little bit more about you all here by launching a poll. So for everyone here, we're going to ask 3 questions just to learn a little bit more about you. And I'm launching the poll right now, so it should be popping up on your screen any moment now. And just give it a couple seconds to show up. And what you're going to see are 3 questions here. And you can actually just click with your mouse which answer it applies to you the most. So the first question being, what is your previous experience level with virtual technical training? By this we mean, over Zoom or WebEx or that kind of thing. Learning over the internet from an instructor. Have you taken a lot of this? Has your team taken a lot of this? Okay, we see the answers coming in. This is great. Thank you. Second question. Have you ever practiced technical job tasks in a virtual environment? So have you basically ever had this simulated or virtual environment where you're actually practicing the task before? Okay, we got great answers coming in, and I will share these with you as soon as they all come in. And then finally, the third question, what is your comfort level about your skills and knowledge about working on electrical equipment? And I'll preface that to say working on live electrical equipment, right? Because that's what troubleshooting is mostly all about, is working on live equipment. What is your comfort level there on that, on your skills and knowledge? All right, good. The questions are flowing in. I'll give them just a couple more seconds. And Greg, I think this will be really great to frame our discussion today, to know who's here on the line. All right, I think the answers have pretty much evened out for the most part. So I will go ahead and end the poll for now. All right, and I'm sharing the results with everyone now on the line. So you should see the window popping back up with the results. All right, so looks like the most people on the line are actually beginners with virtual training. So haven't really spent much time, or if at all, sitting in front of the computer with an instructor via live video chat like Zoom, like we're seeing right now. So good to know, Greg, people who are new to this format. And the next answer here, so 35% of you are beginners. 32%, not too far behind, have some experience, but not much, just a few classes you've taken with virtual technical courses. Only about 9% of you are highly experienced in this virtual format. All right, let's see. Have you ever practiced technical job tasks in a virtual environment? As you can all see, by far and away, no. Most of you have not. 64% of you have not practiced technical job tasks in a virtual environment. So we're really going to show today kind of the ins and outs of doing so in this, and it's really is part of a technical instructional activity today. A few, so 64% of you have never done it, and about 15% of you have done it maybe just once or twice, and another 15% just a couple times. So definitely not too much experience here on the session, which is great. This is the perfect opportunity for us to talk about it and to use it. And then finally, what is your comfort level about your skills and knowledge? We got some experienced electricians on the line here, Greg. So the popular two most answers are the top of the comfort level chart, both at 28%. So 28% of you are very comfortable with working on electrical equipment, and the next 20% of you are somewhat comfortable. And then it goes down from there from 21, 16, and 8 are very uncomfortable working. So most of you have experience with electrical circuits, and it sounds like you have been working on electrical circuits. So now it's really up to us to talk about, and I'm going to stop sharing the results. There you go. It's really up to us now to talk about how can we continue to build and develop those skills, maybe for new technicians coming in the door, new people looking to do electrical work and understand electrical work in a place where we're safe to make mistakes, in a place where maybe there's not the risk of electrical shock, for instance, potentially, but where we can also learn all the lessons we normally would learn with live electrical equipment. So looking forward to learning from you, Greg. Thank you so much for being here, and take it away.
Thank you, Ryan. I appreciate that. So today, Ryan might play the role of the student. He's going to pretend to be a lot less knowledgeable than he really is. And we would typically start, depending on the level of the people in the classroom, we would start with something pretty simple, maybe even more simple than the one you're looking at here. So yes. The first thing we do would be to explain, for example, just how the environment itself works. So we would show them that if you need to turn the power off here, you've got a breaker panel that is labeled correctly, just like everybody's panels are at work, right? And then if we want to take some measurements, we've got a meter there. You can see the settings that are available. One of the things the program is pretty good about, this particular program, Simitech, is giving you little pieces of advice as you go along. That is, if you're on the wrong setting, for example, it'll let you know. So we'll demonstrate a little bit of that as we go along. And if you need it, there's a schematic. Now, one of the things that we almost always do, again, depending on the level of the people, and we're typically starting pretty on the simple side of it, at least start with the simple stuff. And one of the big reasons we start easy is that there are lessons that we can learn from very, very simple projects that you can apply to much, much more complex problems out there in the field. We'll do a little bit of that as we go along too. So we would do a little bit of, for example, explaining where the parts here are in the panel versus where they are on the schematic. So let's go ahead and start with that, Ryan. We're gonna pretend to that you're the student here, and one of the things we've had a lot of luck with is turning the control over to the students themselves individually. And that way they can actually move the mouse around, move the meter leads around. You can see how they would go about it. They get a little actual practice with it. So let's do that now. So Ryan, I'm going to turn this mouse over to you. And if you click once, you should have control. Yep, see if you can move that mouse. Yep, okay.
Yep.
All right.
Got it.
So, first of all, right, could you point to the fuse in the control panel itself?
Okay, it's right here.
And now can you show me that same component up there in the schematic?
Let's see, it's this guy right up here,
Yeah.
the fuse, yes.
Right, so we would do a little bit of that, and when the projects get a little bit more complicated, it's a little bit more necessary. Like we said, what we're looking at here is one of the more simple ones. Not the most simple, but it's down there on that level. So Ryan, let's say an operator comes to you and says, "This isn't working. This whatever it is not working." Where might you start? What would you do?
I try to test if there's power coming in, most likely.
Okay. Okay. So what setting would that be?
The voltage setting.
Yeah, that's right. So what if you were to make a mistake on this?
Oh, let's try this one.
There we go. So there's
Oh, dude.
one of our ones there. That won't do us much good. Yeah, so that's got some of that built in. These are very highly configurable. That means what I'm saying is you can turn these messages on and off as you like. Okay, so it's going to give you another chance. There you go.
AC voltage.
Okay,
Okay.
so you're going to see if they're keeping power coming in.
So I'll grab this black lead and I'll put it over here on neutral.
All right.
And then I'll take this red lead. I think I'll bring it over to the live side, the
All
line
right.
side.
Is that what you expected?
Yeah, I think so. Yep, because I see 115 on that schematic and that matches that. So, yep, that's good.
All right then. So at this point, we're usually trying to see where the students are, what they would do, right? We will save that guidance for a little bit later. It's a really good idea to evaluate where they are as far as their troubleshooting skills, just jumping right into it. So, Ryan, that means we're going to let you go ahead and make some mistakes.
Okay. Let's see. Where would I test next? I think I'll keep
Well,
kind of
if I could interrupt, I
sure,
forgot to tell you,
sure,
I forgot to tell you a little bit more about how it works. So if
sure.
if you wanted to replace a component, let's say you want to replace a light bulb or something,
Mhm.
the wrench, if you grab this wrench here
Okay.
and hover it over the part you want to change, like the light bulb there, now go over to the switch, a switch there. Yeah, if you wanted to change that switch, you would click, go up to the fuse, same thing there. That's right. Now, if you want to put that wrench back and grab a screwdriver,
Okay.
now if you need to take a connection off, you see how when you get close to one of those screws there.
Okay, like this one
Yeah,
on
that's
this
good.
wrench.
So
Oh
there
yeah,
you would click, take it off.
it's
Yeah,
highlighted.
right.
Okay.
Yeah, right. So, okay. What do you think? Is the fuse bad? What are you thinking?
Um, you know, if these lights aren't coming on, yeah, it seems like the fuse could be blown. So
Mhm.
makes sense
All
to me.
right. Grab your wrench, right?
Okay, so I'll see if I can replace the fuse. Grab the wrench, click here, I'll go over and okay, 395 for a fuse. I'll take it. So I click here and don't want to remove the fuse. I just want to get a new one, right? So okay. Oh no,
Oh, that
I did another mistake. Well,
right. So, and the good thing is you're still alive, though, right? You still have
yeah,
pretty good.
I thank goodness for that.
Okay. So we're go ahead and click OK. And so, if you wanted to replace that fuse, you would need to lock it out and tag it out. So up
Right.
there, the breaker. Go ahead and turn the breaker off.
Oh, okay. I see. So it's breaker box. Click the breaker here,
Yeah.
and
And
I like I lock it out.
right. That's
All right.
right.
Cool. All right.
Yeah.
Lock's on there. Good to go.
Yeah. Okay. So I'm going to go ahead and give you a hint since we already demonstrated getting shocked. Right. That we'll have to verify it's dead.
Oh, you got to verify it. Okay, because maybe I hit the wrong breaker or something, right? Okay,
This
so I'll
is
verify. I'll verify
yeah.
that's dead right here. Okay, got it.
Yeah. Okay, now you're free to fool around in there or whatever you want to do.
So let me try to turn on the lights and see what happens. So I'm gonna just hit these switches. Boom, boom, boom. Oh, they're all on and the light won't come on. Okay, let me try these three. Boom, boom, boom.
Hmm.
Won't come on at
Okay.
all. Oh, well, because I didn't unlock the the circuit yet. That makes sense.
Right. Right.
Okay,
That's okay. Program
so
those. Yeah.
yeah. Okay, so I gotta remove the lock. So I'm gonna
Okay.
remove the lock. And oh shoot, I just realized something. My leads are still on there. It's probably not a good idea, right?
No,
Um,
not. If you turn the meter off, it will return them back to their
okay. Okay, yeah,
spot there.
there we go. Okay, now I can turn it back on safely. There we go.
Okay.
All right, so the
Right.
light came on. Well, one of the lights came on, but the other one's not on. All right. All right, so
Hmm.
that, let's see. Well, that light is
Is it
not
a
much.
blown fuse, Ryan?
Well, I can say that it's not because the fuse powers everything in here, and that one light's coming on. So I guess I just replace a fuse for for no good reason, right? But hey, I'm figuring out that's not the issue, I suppose.
Well,
Um,
we do talk a lot about that in the class. We talk about throwing parts at a job. It's not really the most efficient way to go about troubleshooting. That's right.
yeah,
So, okay, are you back to taking measurement?
yeah. Let's try to measure some voltage again. So I'll go to voltage. I'll take this black lead, put it on neutral. Take the red lead, put it on the bottom of the line side uh, here, because that's the next one. Okay, 115. So that's good. That means we still have power. So I'll just follow that wire over to the fuse. The right side of the fuse here. There we go. 115. That's good. Other side of the fuse is next, and 114.9. Pretty good. We still got power. I'm gonna go. I guess I got to go to this S1 over here because um, that's on the way to the bad light. Go here, 114. Um, go to the next one on the other side, and I'm gonna see 114. Okay, that's good. I still got power. Um, here. Okay, still got power. I'm gonna go to here. I'm happy. Continuing going the systematic way you taught me earlier in the class. Okay.
That's right. Sometimes that works. Sometimes
Yeah.
that works. Beginning to end is this particular way of going about it. Yeah.
Yeah, I'm kind of going slow at it, but I'm slowly getting somewhere. It's still live. Okay, it's still live. Wow. Still live. And then I'm going all the way to the light itself.
Ah,
And it's still
ah.
live. Okay. I got power all the way to the light, but the light's still not coming on. I think
Mhm.
the light's probably not good. The bulb's probably blown out or something on this light is my
And,
guess.
and you might be right. You might be right. However, does that light bulb need just a hot, or does it need a hot and a neutral?
That's a good question. It needs a neutral too. Yeah, every hot needs a neutral.
So that's right. So we verified that there's a hot there, um, but we haven't really verified that there's a neutral.
Oh,
Now,
okay.
if we verify there's a neutral there too, and you get 120 volts to that light, then you were right. It's a bad light bulb. So we found out that there was a hot there by leaving one lead on neutral and moving our hot lead around. How would you find out if there was a neutral here, meaning a good neutral, a neutral
Uh,
all the way to the light bulb?
I think I can try to test across the light. So
Mm-hmm.
I'll bring
Okay.
the black
Okay.
lead across the light, and if it was a good light, it would go. I'd get a full voltage, I think. So let's see.
Aha.
Ah, I don't have anything.
That's right. So what did you learn? You've got a hot there, but
No neutral. I see.
okay. So the bulb is probably fine. We saw there that it looked like it was a bad bulb, but we found out that, well, if there's no power there, it's not really power there unless you have a hot and a neutral. Yeah. So at this point right there, we think it's a neutral. So if you want to verify that, we see the one right above it. Go ahead and point to that one right above. That's right,
Yeah,
and
this
then
guy.
trace.
Uh-huh.
Yeah.
So this is the line that connects the two lights to the neutral.
So if we want to fix that, of course, you'll need to go lock it out and tag it out. Do
Hmm.
that real quick.
Okay, so I'll click here. I'll lock it out, and then I gotta verify this time. There we go.
Right.
Learn that
Right.
the hard way. Okay.
Yeah, okay. Now, in order to replace something, if it's a component, you just hover over it with your wrench. But If it's a wire, you need to take one end of that wire off. So go ahead and get your screwdriver.
Okay.
All right, I'll take that down and take one end of that neutral off.
Okay, so I'll do this right here. Oh, the wire came
And
out. I see. Yep.
now, since the power is off, you could, if you'd like to, and we're pretty sure it's that wire, right, or connection, but you could, if you want to, verify it with an ohm meter now that the power's off. So you could change your setting on your meter.
Okay, I'll go to ohms here.
Yeah. And then take one lead to one end of the wire.
Mm-hmm. Okay.
And the other lead to the other end of the wire. Perfect. Good
So
job.
now I can actually attach to this little wire end. Got it. Okay.
There, yeah.
Yep.
Ah, there we go.
Mm-hmm.
There we go. Yeah.
And I'm seeing OL.
Yeah. And we would have already discussed, of course. Like we discussed earlier, Ryan, OL means what?
Oh, yeah, it means overload. Just kidding. It means open line.
Right. Okay, so you can turn your meter off, get your leads out of the way. And now you can use your wrench, and you'll have to get that wrench really close to the end of the wire to light it up.
Okay.
That's it. Click.
And now I'm going to replace this part of wire. Okay.
All right. Now, think you're ready to try it?
All right. Let me try it. So I got to unlock it this time to start with. So hey, I'm doing better already.
It's always good practice to turn your switches off before you turn something on with the breaker. So let's go ahead and turn the switches off first.
Oh, yeah. Okay.
Probably wouldn't matter with light bulbs, so we don't want to turn things on with the breaker unless we have to.
Right.
Okay.
And I'll go over here and I'll remove the lock. And then I got to turn it back on. Okay.
All right. Ready to try it?
Ready. So I'll try to... Yeah, stand back. Again, a good reason why we're in a virtual environment right now. Okay. On. Hey, it turns on. So I could have replaced that bulb all I wanted. All right. And it would have been bad. Okay.
Yeah, very good. Very good. Okay, right. So this was an example of a pretty easy one. The next step we would probably go from here in a normal, one of our typical troubleshooting classes that's not extremely high level troubleshooting. We work our way up to this stuff. We would probably at this point go right to something with relays on it, right?
Mm-hmm. And I'll also make a comment to say that you all may have noticed that the module racks up a bill. So basically it racks up the amount of dollars the individual who's taking this is spending, as well as the amount of time. It says there's a time associated with each task. So that'll take about 20 minutes of the technician's time. It might take an hour of your time to replace this component. Those add up too. So by the end of the session, you can kind of get a metric for performance of troubleshooting based on how much money they threw at it before it was fixed, right, Greg? And then how much time was sunk into, that simulated event before it was fixed. So it's kind of a interesting way for the supervisor or for the training coordinator to track how people are doing in these simulations. So that's kind of a fun aspect. I like that it puts a dollar sign on the light bulb, and you're like, just wasting money at that point, which is good. It's good. It's a good way to kind of track that. All right, so I'm seeing a different circuit now.
Right, and to somebody who hasn't seen this before, it might look a little intimidating. So Ryan, I'm going to take control of the mouse back from you there.
Okay.
All right, I've got it. And one of the first things we do is make sure that the student understands how to actually read this schematic and interpret how it's supposed to work. What is this supposed to do? If we look at this, we see on and off buttons, and it looks pretty obvious. If we push on, the lights are going to come on, right? We think that's what's going to happen. But if we take a look up here at the schematic, we see that these are momentary buttons, which of course we've already talked about that. They already know what this means and the symbols by this point. But we do need to explain how the circuit actually works. They're momentary push buttons, so do the lights just come on while we have our finger on the button and then go off when we let go? Well, let's see how it works. So we would say Assuming we do have a good neutral over here to everything, we turn the power on. If we have a good fuse, let's see what happens. We see that we're getting power to anything that's, and anything has a wire on it, but all these components are normally open. The contacts, the push buttons, they're all normally open. So that's really as far as we can get if we just turn the power on. But if we push any of these on buttons, which are normally open, we'll see here that if we push this one, we're going to get through that button, through all the normally closed push buttons, and energize the relay coil. Now, that's R1. So any R1 contacts associated with that relay are going to change state. Well, here's a couple down here. We have two of them that are both normally open. Well, the first thing that happens when we energize this coil is this set of contacts changes state and the lights come on. That's what should happen. We've got our finger on the button now, right? And the lights are on. In addition to that, this set of contacts is going to close as well. And what we're going to see is a second path to that coil. And what that allows us to do is take our finger off of that push button there, like this. It opens that up, but we still have power to the coil. That's a holding circuit. This is their first introduction to a holding circuit, or it might be called a seal-in circuit, depending on where you are and who you talk to. But it's also a really good introduction to motor control circuits, because we're going to be seeing motor control circuits with holding contacts. That's very, very typical. So here they've seen something that is it's very, very normal, very, very standard in the industry. So let's see what happens if we push a stop button here. It'll open up, break the power to the coil. Once that coil goes back to its normal state, the contacts go back to their normal open state, and the lights go off, and we're ready to go again. So depending on the crowd, might go through that a couple times, make sure everybody understands it. We would do that thing about, hey, here's a component over here on the panel. Where is that over here on the schematic? Make sure they understand all that. And then we're ready to troubleshoot it. Let's get rid of some of those extra lines there. And Ryan, I am going to turn this over to you.
Okay, got my mouse ready. Got my mouse ready to go.
Good. And so it's all yours.
Okay.
Go ahead and tell us what you want to do here.
Well, I guess I can try to turn it on and see what happens. So
always a good first step.
Press on.
Yeah.
Okay, nothing happened. Try this one. No. Okay, try this one. Well, I'm not having much luck, that's for sure. Nothing's really happening. So guess I got to start troubleshooting, don't I?
And I would like to show you a technique that's pretty effective on this. I'm sure you would check power coming in first, right? Is that what you're about to do?
Yeah, that's what I was going to do, line to neutral again.
All right.
So I'll click here. I'll bring the black lead up to neutral, and then the red one up to line.
Mm-hmm.
Okay, that's good.
So
yep.
The last time we traced through the circuit from the beginning to the end, and that can be effective. But many times a control panel like this will have power in the box like this, and then the wires will leave the enclosure to go out to the field, meaning that's where out in the field outside the box, that's where your limit switches and proxies and things like that are, right? That's really kind of what we're recreating. Then after all those devices, it comes back into the enclosure, maybe here. So something that's very effective is starting at the beginning, which you just did, and then go right to the end. What is it we're turning on? Now, you might think it's the light bulbs here, right? You might think it's the light bulbs. But what are we really turning on with the push buttons?
We're turning on the lights and the relay as well. Yeah, really the relay's got to be energized for anything to happen.
Right, so here's this technique. I'd like you to take the red lead and point for me
Okay.
Where you're checking on the hot right now, point on the schematic, please.
Okay, I'll take this red lead. I'm going to be testing right up here at the very top. That's where I'm at right now, or at least where I was. Yep.
That's the beginning. The end is what we're turning on. So can you show me on the schematic where you would go to check to see if we're getting power to the coil, for example?
Oh yeah, so I went step by step by step, and now I could probably just go right to terminal 2 right here on the relay. And
That's
if
right.
I have
Now,
voltage there, that means everything else before it's good. Is that right?
that's right. Now, if there is voltage, we've saved a bunch of time. If there isn't, we still know it's out there in the field somewhere. So um, show me where that is down there. Go ahead and test in the control cabinet there.
Okay,
The
so
actual
the
relay.
schematic said it was terminal 2, so I gotta find that. It's right here. Okay, perfect.
Now,
All
why
right.
don't you? What else do you have to do to get power there, though?
Oh yeah, everything's open, so I gotta press a button. See if I get power.
Right,
Right.
right. Okay. Now these are momentary, so can you push and hold it down so we have time to see the meter? Ah,
Okay.
there we go. So we just saved a bunch of steps, didn't we?
Thank
We just saved it
goodness.
this time. This time we did. Doesn't always work like that. Okay. Now,
Okay.
what did you do last time to see about yeah, on the light bulb? The last one. What did you learn about the light bulb? It takes a hot, but what else?
Neutral as well. Yeah.
Take the same approach.
Okay. So I'm gonna go across the um, relay to start with. So that's 2 to 7. So I'm going to go over to 7. Oh,
All right, that
there we
was a little advice we don't need right now.
go. Sure. Okay, 2 to 7 gives me 0 voltage. That's,
What?
yeah, we learned that last time that if we get a 0 voltage across something that should have a full voltage, that means something might be wrong with that neutral potentially.
Except that, how do we have to get that
Oh, that's
voltage?
right. I got a false 0 because I'm not pressing the button yet. So let me
There you
press the
go.
button.
Okay.
Okay, here we go.
Can you push any of them?
Yeah, let me try this other one here and see if it does anything different. Oh, I
Aha.
do have a full voltage across that coil. Okay.
So this, yeah.
So,
So you got
so,
voltage.
yep, I got the
Yep.
full voltage. I think that means the neutral's good, right?
It does mean the neutral's good. Now think
Okay.
about it. It's no different than the light bulb. If you had full voltage to the light bulb and it wasn't on, bad light bulb.
Hmm.
Full voltage to that relay and it's not working.
Yeah, maybe the relay is not working at this point.
Right.
Now I can go back to the
Yep.
component itself.
We're pretty sure about that. So I tell you what, go ahead and lock it out and tag it out.
Okay. Boom, boom.
Live, dead, live.
Live to live, verify.
Mm-hmm. All right. Now, it would have been maybe good practice to get our meter leads off, but here's what I'd like you to do. I'd like you to check to see if that coil is good with your own meter. That is, go up there to the schematic, show me. Yeah, that's where you would check with your own
Yep,
meter. But
right there.
it's also really good practice to take a wire off if you're going to check something like that, because you might be reading through another part of the circuit.
Good
Can
call.
you get your screwdriver?
Okay, take my screwdriver up here on top,
Yeah.
and
All right.
I'll unscrew the terminal for number 2.
Yeah.
There we go.
Now, can you check with your own meter across 2 and 7 and tell me what you expect?
Okay, ohms. Go.
Well, tell me what.
Oh,
What
I should be reading something because a coil has some resistance. It's a device. Let's see.
but you
So,
don't.
there we
Okay,
go.
so there you go. So go ahead and quickly change out that relay because the clock's ticking, right? We're trying all
Sure.
these jobs. PM, it's okay. Time it's
Right.
due.
That's right.
So you'll,
It looks.
it's like,
Yeah, it looks like at the top of this, we've already spent 11 minutes trying to fix this issue. That's interesting. So I'm going to come back to that actually because I'm curious about it. Okay. Okay, I'm over the relay. 39.95. Ooh. Okay. Replace.
yeah, don't forget to put your wire back.
Oh yeah. I get my screwdriver, screw it back in again. There we go.
So you could have checked that coil to see if it was good or not with your old meter, right? The new one would have been a bad idea. Just in the interest of time, let's turn it on, smoke test it.
Okay.
Ready?
Yeah, right. See if they let the smoke out. So let me remove lock. Let me turn on. And let me go to turn on. Yeah, let me press this on button. Boom. Hey, that's good. And I'm letting go. Yes, they stay on. That's a good thing.
Yeah. Well,
Cool.
it's a good idea to check them all.
Yeah, I think so. Make sure each of the 3 on and off stations around work. Okay. Yep. And then off. All right.
Yep. And a
We're
couple of those, and the class would progress to probably motor starters, and then we would do some motor control troubleshooting. And depending on the class, we can go to PLC simulations. Those are also pretty good. So I can't wait to see everybody's questions. Yeah,
Yes. Me too. And just to remind everyone, this is a live session. So we got a couple questions coming in. We got a few already, but definitely this is your time to really start asking those questions based on what you're finding curious or what you have curiosities about. The Q&A line, it's called Q&A button. Click there, type in your questions, and we're going to answer as many as we possibly can. So that concludes the technical demonstrations. What do you think about this virtual environment, Greg, as we kind of get started to ask questions on its kind of educational nature of help learning the electrical trade?
Well, when we first started using these, I had my doubts because we're used to doing things in the classroom, and our troubleshooting classes were very, very hands-on. I was wondering how we're going to replace that. I've been so happy with this that we've had discussions about when we get back into the classroom using this software in the classroom to complement the other hardwired things. In the classroom we use, there's a lot of class time eaten up building these circuits. It's great to have hands-on. Most guys really need that hands-on. You can't learn a lot by somebody talking at you. All right, so the lecture format isn't great. It's even less effective with the online. So this is a way that people can actually get in there, do it, see it, understand it. I've been really, really happy with it. Yeah.
Excellent. So it's kind of a way to test in a safe environment, right? I mean, electrical troubleshooting is the first thing we all learn in the classroom or any other format for electrical is electricity can hurt and kill you very quickly. And so that makes us maybe a little bit hesitant to try out some of the methods of testing inside these panels a little bit because it's, you have to have all the safety training before you do it. Well, this gives us people an opportunity to do that. And I appreciate it. I was able to make some of these mistakes where I could have caused something bad to happen, but I didn't. So I appreciate you walking me through that, Greg. Thanks so much. Now, I got a really great question coming in here on the line and a couple others starting to flow in. So I guess the fundamental question here, what the heck program is this, right? Well, you had mentioned it at the beginning of the session. It's called Simutech. It's a TPC product based out of Canada and also the United States, where we have these circuits that you saw here, but it continues to build upon that in this virtual environment in our classroom and also in self-guided format. So these are designed to be self-guided as well. Simutech, right? Simulation technology, I guess it makes sense. So that's great. Also, there's motor control circuits, PLC circuits built into these, as well as some safety related content in 2D. In this format we showed you here, it's the easiest really to digest in the classroom quickly. We also have a whole 3D environment troubleshooting module available as well. So there's kind of a lot out there to play with, and it can take hours upon hours to get through these troubleshooting steps. One thing also I want to make note of these questions is the time, right? So Greg and I took about 18 minutes to get through these troubleshooting scenarios, right? Now that's kind of funny, right? We're walking through it, we're getting through it now. I want you all to think about how much a minute, or let's say how much 1 hour costs your company of downtime. And so that's one thing that I find these timers in the simulation to be really cool because, hey, let's say we ended up taking 20 minutes to troubleshoot this issue. If we could take that 20 minutes and by, practicing, get that down to 10 minutes of troubleshooting time, how much is that 10 minutes saved going to save the company, right? Well, it all really does depend, but I tend to ask this in my classroom, Greg, I'm sure you do too, is how much does it cost you for an hour of downtime? And what kind of answers do we get, Greg? Well, what are some
Oh,
numbers you get?
$250,000 is not unusual. They'll
Yeah.
usually say which machine.
Yeah, exactly. Which machine? And then you say, pick one. And then they're like, quarter mil. Yeah. $10,000 an hour per machine. And we have 20 machines, that kind of thing. Yeah. I've never heard less than $10,000 an hour. On any response I've gotten, because these machines have huge throughput in manufacturing environments, and in the case of other commercial people like schools or hotels or that kind of stuff where they're not pumping through machines and products, they lose revenue, right, for every second or minute of downtime of customers. So $10,000, right? You take that 10 minutes of time, that's thousands of dollars you save by just saving 10 minutes of electrical troubleshooting time to get the machines up and running. So that helps really kind of understand these. It's a great question. Here's a really good question. You ready for this one, Greg? What is that OL? So we talked about OL, and I jokingly said overload, but it's open line, right? There is, the occasional disagreement that it stands for something else, depending on the manufacturer. However, what does that open line mean? What does OL mean on a meter, and what's its importance in? And does changing it to ohms cause that to happen? And what is its meaning?
Yeah. So the people that say it means overload or sometimes out of limits, they can be right. For example, if you have it on voltage and your meter will handle 600 volts AC, and you put it on 1,000 volts, assuming your meter doesn't blow up, you might see an out of limits on there, OL for out of limits. But most people, when we'll see that when we put our meter on resistance, that is, we're looking at to see how many ohms something has, right? So if your leads are apart, your meter says OL, meaning open, like an open door or an open switch. And then when you close that switch, then you see some kind of resistance, low resistance maybe. So a burnout light bulb would say OL across it. A blown fuse would say OL, open line, open loop, technically open loop, because that's what most manufacturers say in their documentation, open loop.
Gotcha.
Yeah.
Well, thanks so much, Greg. Here's another really good question about the relay activity we just completed. Agree or disagree with this? If Ryan read 115 volts across that coil, and then the coil is open, right? So if Ryan read 115 volts across that coil, then the coil is open, and no need to de-energize and check continuity across the coil. Agree or disagree?
I have to agree with that. That would not have been necessary. It would have been a pretty good idea to check the new one.
Sure thing. Yes.
Yeah, before you put a bad part in. Yeah, but absolutely agree with that. Yeah.
I would comment that sometimes in the electrical troubleshooting class, what should you read across the coil for voltage if it's working properly?
That's a very interesting question. And it's the same answer as almost any electrical question. It depends. Right?
Yeah, right. Yeah.
Answer, it depends. And in our case, it depends a lot on the size of the relay and especially the voltage of the coil, voltage that the coil works on. Mm-hmm. For example, if we had measured the resistance of that one that works on 120 volts, we would have got over 1,000 ohms. And I have one on my bench here somewhere. Yeah, this thing here, right? More along the lines of a 24 volt coil, more along the lines of 70 some ohms. Yeah, so that's a big part of it. Good question.
Definitely. Do you know, Greg, in this in virtual environment, is it possible to add our own circuits and faults in there? Let's start with the faults. Is it possible to add our own faults into these circuits?
The short answer is no. But it has so many of them built in. It's hard to find something that's not there. That is, for example, the open neutral. I really like to use that. There are several there with that. Or you have a bad coil or a burnout light bulb or a bad connection between two components or a bad component. There are hundreds and hundreds of them built in. You can't make your own, but you can pick the one you want to use. Yeah,
Good
you
call.
can.
R1, the R1 relay was called a latching circuit. Does that sound right? Is that a good term to call this the circuit?
Well, I try to avoid that word, the word latching, only because a latching, there are things like latching relays, and a latching relay is something different. That's a different thing than what we were looking at. I will also call that a latching circuit, but in the classroom, I try to avoid that just so I don't confuse people. I mentioned earlier, it depends on what part of the country you're from. It depends. I mean, if I'm down in Louisiana and they said it's a ceiling circuit, it's a ceiling circuit. What else would you call it? You know,
Right.
and it really depends on the people, how old they are, where they've been. Yeah.
Definitely. Great question here. Uh, so it was something I actually caught too, that why wasn't the black wire designated a neutral in that last circuit, in the relay circuit? Both line and neutral were black. That never happens in the field, right, Greg?
Yeah. So one of the things they try to recreate is a real control panel, and it isn't unusual at all to see an industrial control panel be, you know, all red wire or all black wire. All the control is red or black. Even when they get into DC, where it's positive and negative, you think red and black, you know. But as it turns out, well, not necessarily. So I would I would say lots and lots of times they do have a white neutral, but you can't count on that. You can't count. And then when, you know, not everybody uses the same color code that the United States does too.
Indeed. I think I can field this question and definitely help me here, Greg. But what is the R1 slash R2 in that schematic we saw earlier? It seems to be an open circuit, but the lights were still turning on. So those were absolutely an open circuit to begin with, or what we call normally. So what I think we were seeing was normally open contacts that don't allow the current through to the light until they get closed by that relay through the power of the magnetic action of that coil closing them. So what you see in the schematic, yeah, right there at the bottom, R1, right there, it appears open, and that's absolutely true. It's open if it was just sitting there not energized, but as soon as we get energy to that coil of R1 up there, yeah, then we have the ability to close both of these R1s here, and it allows power to the light. It's kind of a way to basically automatically flip a switch without you having to walk up to a switch and switch it. It just does it automatically for you.
Mhm.
All right, good question.
I told you guys that Ryan was just pretending to be green with this.
I try to, I always have something to learn, Greg. There's always new ways to do things I learn. I love that. I mean, that's what's kind of fun about these activities too, is you're never going to approach them the same way twice. And one technician on your team, let's say your night shift, is going to approach it way different than someone on the day shift or whatever it might be. And I think
Absolutely.
that's the beauty of this kind of ability to let people do it for themselves.
Absolutely. One of the things I found out as soon as I started using this was that different people have different approaches to it, and it's good to see those. It's good to see somebody do something different than you would. There were many times when I first started this where I would say, "Well, how would you approach this?" And I want to stop them and say, "No, that's wrong." But then I watch them go through, and it's like, "No, that's not wrong. That's just different." You
Yeah.
know, and it's really good to see how different approaches can work with different types of problems. It's really education. Me too. Everybody that's there learns something like that. Yeah.
And kind of to piggyback on a previous response on this question is, can we create our own fully customized circuits? No, but I think the amount of different types of circuits we do have in here, from motor circuit to a PLC circuit to relay powered control circuits, lighting circuits, really gives a lot to chew on. Not to mention, from there, we actually get into some industrial control circuits where it's actually in the field with a real garage door opening and closing, and you got to go to different panels and try to type in a password, and it's not working the right way. And there's a bunch of different ways to use this understanding of circuits.
So we're showing here just all these are just on one module. This is just on one module. It gives you the what's wrong with it, what doesn't work, even how much time it should take to fix it. It's really just goes on and on, just really dozens and dozens per module.
That's the user manual, is that right? Are you looking at?
That's right. And that's not available to everybody. I mean, if you download the program, it is, right? Sure.
Let's see. Got some other great questions coming in. I'm going to try to get to as many as possible in the next 10 minutes or less, but I love this. This is what it's all about here. Let's see. Can you demonstrate a Megger test? We can, and we do in the classroom. Unfortunately, we don't have time on this webinar, but we actually have a simulated Megger test where we have 4 different motors. Each are going to give different readings that seem good at the time on the regular resistance, but when you do the meg ohm resistance, something's not quite right. So yeah, that is available. Unfortunately, we can't jump into it and download it right now and everything, but it's out there for sure. We got to press that test button on the meter, and that's another one. It's another example of, I've been shocked on a meg ohm meter pumping out 500 volts when I was touching it on accident. It's no fun. And in this virtual environment, you don't have to worry about that, but you still can learn from your mistakes of, picking the wrong motor to put into service, or picking the wrong one that's actually broken as the correct motor, so to speak. What is the 3D version of the simulation? So you see this lighting one right in front of us? This one is made 3D, as well as another motor control circuit is put into 3D. Basically anything you see in this 2D flattened format, you're also going to see in another version on 3D, built in a 3D environment where you click and you kind of walk in remote. Hey, you did it, Greg, look at you. You actually did it. So here is that Megger activity, by the way. So I really thought we didn't have time, but we do. So basically, this is a interactive activity simulation where here you go, you got the Megger, you're dragging the leads around to the different leads of this motor housing. And then you can turn it to either meg ohms or regular ohms, whatever you want to do to test the motor, and it'll give you the readings, and you got to figure out what to do next. So yeah, you press that and see what happens. Oh, greater than 100 mega ohms. Is that good? Is that bad? We get into all those details in group activities in the class for sure. Electrical troubleshooting class, we talk about megometers. We talk about it in our motors and control circuits class, as well as a little bit in our basics of electricity and advanced electrical troubleshooting classes. Motors, drives, and troubleshooting. Yes, yes, and yes. So there are motors, there are drives, and there are PLCs to troubleshoot in this virtual format, and it makes it that much more interesting and fun. Not to mention, you can troubleshoot the wires about the PLC, which is half the battle. But then you can also jump into the PLC program, the programming of that PLC in the PLC simulator that we use, and start reprogramming some of the functions. So there's a lot to play with, and Greg is our PLC guy, so he knows what it's all about to program these PLCs. And what we actually end up doing a lot of times is we have a PLC that's right there in the room with Greg or the instructor, and we can program it on the fly, and actually it'll change the way it flashes its lights or does its job right in front of our eyes. It's kind of fun to see that. Let's see. One of the first questions that came in, I forgot to answer. I want to make sure it comes in, and that is, do you have modules that can be used to test potential hiring of candidates' electrical knowledge? So basically, right on the front end of someone's journey at a company. And my reaction to that is absolutely, yeah. So I know a company, the manufacturing facility I worked for before TPC Training, we did a mechanical aptitude test, and a little bit of electrical aptitudes for our technicians before they came in the door, just to kind of test their abilities as part of the human resources process. And if they were able to sit down in front of one of these and kind of the interviewer, let's say the maintenance manager, could kind of pick their brain and see what their troubleshooting method is like. I mean, if any maintenance managers are on the line right now, I'm sure you could see a lot of value in seeing how they think and how they go through issues in a comfortable environment instead of dealing with $1 million equipment and finding out the hard way. Greg?
And another thing that I talk to managers about over the years is when they can test them, and you know, it used to be on paper, but one of the things they find out is where are there holes in their knowledge. They might be an experienced guy, but where are their strengths and where are their weaknesses, right? Because and then they can get the right person. It's not a pass fail kind of thing. That's what I really mean. It's very useful to find out. Well, okay, this guy knows his motors, but he's a little weak in control, or the other way around.
Mm-hmm. Absolutely. Yeah. Great question about the 3D version versus the 2D version. What does the 3D version add to the simulation, right? And it really is just that it simulates more, right? It makes you really feel like you're there a little bit more in the terms of where you have to walk up to the panel and get close to it, and then you can kind of look around the different aspects of each individual component before you decide to replace it. So it's just a little bit more immersive of an experience, but you're still getting all the same components and learning done. It's just in a different format. It really is. It depends on the learner. At the same time, it's a little bit more complicated too, right? There's a little bit more than just 2 ways to go. There's 3, right? So you can go back and forth. You can walk over to the panel over here, and you got to manually walk over to lock something out and then go back to the panel. It's basically a lot more steps to get the job done, but it's also, that makes sense because those are the steps you have to take. So if you're trying to get someone that baseline of knowledge in one way versus another, it just depends on the learning style of that person. It really does. And quite frankly, computer skills, right? So, you have to use more of the mouse and more clicking and navigating in a 3D environment and in this 2D environment. It takes a little bit of learning curve, but that's really what these user guides and the instructor guidance is all about as well. Is the timing, so we talked about timing, is the timing based on how long you take in the classroom or how long it would take in the real life scenario? So, this relay will take 15 minutes of time. You're absolutely right about that. It is a estimate by our instructional design team that built this session out, where it's a typical average that our expert like Greg have estimated this job to take. Can it take longer? Can it take shorter? Absolutely, especially when some people are quicker at repair and screwing things in than others. But it's kind of more of a game mechanic than anything, right? Where you can play around with the times. Everyone has the same bar to pass, and see who can spend more time or less time fixing their issues than other people. Let's see. Interesting one. Maybe we can end with this one, maybe one more, Greg, and that is, can you explain, or maybe explain why not? Can you explain why some systems don't require a neutral?
Sure. Some of them might be 220 volts, for example, where you have 2 hots. Think your house, right? You've got a dryer in your house. That's if it's electric, that probably has 2 hots to it. Best example is probably an electrical water heater. There's no neutral to that. It's 2 hots so you have 220 volts. Another one might be DC, where you have positive and negative. Sure.
Good call. Not to mention 3-phase, right, Greg? Brown, orange, yellow, let's say. Those are all
right.
hot, but then they kind of act as each other's neutral, maybe. But there's no white wire necessarily on that motor.
Right.
Okay.
It's a return pad. It's still a return.
Yeah.
I might refer to return, but yeah, sure. 3-phase is a good example. 3-phase motor doesn't need a neutral. Yeah. Yeah.
Well, this person gave me the perfect segue, so thank you, Larry, for this last question, and that is, Ryan, when is the next course training? When is the next webinar we're holding? And so basically, the next webinar we're holding is in 1 week, exactly 7 days from today, and we're going on pretty much a 2-week clip through the end of the year on a bunch of these similar topics that you're seeing today. So basically, this one's about electrical troubleshooting. Next week's is about HVAC, the tools for HVAC technicians, like gauges and how to use them. We're going into on-the-job training, how to really do the best type of on-the-job training. A crash course on how to read schematics. A bunch of you were asking about the schematics. I'm sorry I couldn't get to some of those detailed questions, but we have a whole crash course in reading schematics on this free webinar that we're going to have before the holidays, and a bunch of others out there. So go to our webinar page on tpctraining.com. You can take a look, you can register. And you see here, if you have more questions, this is a fairly complicated kind of platform we're talking about here. There's a lot of aspects to it we weren't able to even start talking about. So if you have questions about training, about instructor-led training, about Greg's credentials, about my credentials. If you want to talk to me, if you want to talk directly to Greg, or if you want to talk to any of our team of expert consultants here at TPC, email this email, sales@tpctraining.com. It connects you to our whole team of client service consultants, as well as call this phone number. You're going to be talking to our VP, or you're going to be talking to any one of our account executives across the country and get to know more information about this. And feel free to connect directly with me at rsmith@tpctraining.com as well. So thank you all for being here. It's been a pleasure having you, and have a great day.